You ever kind of get stuck on the thought that, like, our ability to even think, reason, have consciousness could all be, like, tied to the fact that we have these bodies? I mean, that we're physically in the world.
It really makes you question some pretty fundamental stuff.
It does.
Yeah.
And I feel like that's the perfect segue into what we're diving into today, embodied cognition.
Yeah, definitely a big shift for cognitive science. And for you, dear listener, who I know loves a good philosophy puzzle, embodied cognition really makes you rethink things like knowledge, the self, even that classic mind-body problem.
Right, like for so long we've thought of the mind separate from the body, almost like software running on the brain.
Right.
But embodied cognition comes in and says, hold on, the body is part of how we think, not just this vessel.
Exactly. And that's what we're unpacking today, the core ideas of embodied cognition, the evidence they've got, and what it all means for understanding ourselves and the world. And this isn't just saying niche theory, It's having a ripple effect across psychology, neuroscience, even robotics and AI are getting in on this.
So before we get too deep, let's set the stage. We need to understand what embodied cognition is pushing back against. And that's traditional computational cognitive science, right?
Right. That's sort of the classic view. Mental processes are basically computations. The brain is like a computer. And cognition is all about manipulating symbols based on rules.
Okay, help me out here. I'm picturing a computer with, like, inputs and outputs.
Yeah.
But how does that translate to thinking?
Think about it this way. Information comes in through your senses. That's your input. That input gets turned into symbols. Imagine, like, a language only your mind understands.
Okay, so kind of a mental code.
Exactly. Then your brain takes these symbols and, following specific rules, manipulates them to produce some output. It could be a thought, an action, a spoken word, whatever.
So it's all very step-by-step. Input to symbol, mess with the symbols, get an output. And this is happening all inside the nervous system.
You got it. And for a long time, this computational approach was huge. Influenced Chomsky and language, Broadbent and attention, Newell, Shaw, and Simon on problem solving. Even memory research with Sternberg and perception with Moore all build on this idea of the mind as a computer.
And this mentalese thing, that's a big part of this, right?
Yeah.
That there's this internal language of thought, like computer code, that our brains use.
Yeah. Basically, understanding how the mind computes was thought to be the key to understanding cognition itself.
Okay, but like any good theory, there are folks pushing back, right? Laying the groundwork for what would become embodied cognition.
Absolutely. And one of those was ecological psychology, spearheaded by J.J. Gibson.
Ecological psychology.
Yeah.
Okay, what was Gibson's beef with the computational approach?
Well, he took issue with the idea of impoverished stimuli. That was a big thing in computationalism. The idea that the sensory information we get is limited, incomplete. So the brain has to do all this heavy lifting to fill in the gaps, make inferences, and actually construct a perception of reality.
I've heard that. Like how our eyes only get a 2D image, but we see the world in 3D, so the brain has to use all sorts of tricks to figure out depth and stuff, right?
Right, or think about language acquisition. Chomsky said the input kids get isn't enough to explain how quickly they learn. So computationalists said there must be all this innate knowledge and processing going on. But Gibson said, whoa, hold on. He said the information in the environment is actually incredibly rich and structured. But you got to consider the organism interacting with it, not just passively receiving data.
Okay, so it's not just the information itself, but how the organism is moving through the world, experiencing things.
Exactly. Our movements, our senses, they all create these dynamic patterns. And within those patterns are what Gibson called invariant features. These are aspects that stay stable and directly tell you about the environment without needing to make inferences or build complex representations.
Can you give me an example of that, like how an invariant feature would work?
Think about how you see the shape of a square, a computationalist might say. Well, you see a flat image on your retina, and then your brain uses its knowledge of perspective and geometry to figure out it's a square.
Okay, makes sense.
But Gibson says, nope. As you move around a square, the way the light bounces off it, the way it changes on your retina, that pattern is different from how it'd change if you were looking at, say, a diamond. So the way the sensory information changes, that's the invariant feature. And it directly tells you it's a square without needing any fancy mental calculation.
Okay, so by actually being in the world, moving around, The information becomes much richer than just a static image.
Right. And that idea that the organism and the environment are intertwined, that's a huge influence on embodied cognition. And then comes connectionism, which in a way messes with our idea of computation itself.
Connectionism, that's all about neural networks, right? Like how our brains are wired up.
Exactly. So instead of thinking about a central processor manipulating symbols, connectionism is all about networks. Nodes connected together, sending signals back and forth.
Okay, so it's still processing information, still computation in a sense, but it's not using symbols and rules in the same way that traditional computers do.
Right. It's less about a program with specific instructions and more about the pattern of activity across the network. Hatfield actually described it as non-cognitive in the sense of not having those symbolic representations.
So it's still computational, just not cognitive in the traditional sense.
Exactly. And that opened up a new way for embodied cognition folks to think about mental processes. And this is where dynamical systems theory enters the picture because those networks aren't static, right? The activity is always changing.
Right, it's like a constant flow.
And dynamical systems theory gives us the math to understand how that flow works. Plus, it's not just about the brain in isolation. Dynamical systems can help us understand those back and forth interactions between brain, body, and environment.
So we've got Gibson saying the environment is rich with information. We've got connectionism offering this alternative way to think about computation. What was that third influence you mentioned earlier?
Ah, yes. Phenomenology. That's a whole branch of philosophy that's all about conscious experience, what it feels like to be in the world, you know? The texture of time, the way we experience space, the feeling of our bodies.
So less about building models of the mind and more about really paying attention to what it's like to experience things.
Exactly. And folks like Heidegger, Husserl, and especially Merleau-Ponty, they really emphasize the role of the body in shaping those experiences. They were pushing back against that Cartesian idea of mind and body being totally separate things.
Oh yeah, Descartes, the I think therefore I am guy.
That's the one. But these phenomenologists said no, our bodies aren't just containers for our minds. They actively structure how we perceive, understand, and engage with everything. Merleau-Ponty even went as far as to say consciousness itself is embodied. He had this great quote. Insofar as, when I reflect on the essence of subjectivity, I find it bound up with that of the body and that of the world, this is because my existence as subjectivity is merely one with my existence as a body and with the existence of the world.
So basically, you can't separate the I that's thinking from the I that's a physical being in the world. They're one and the same.
Exactly. And that has big implications. It means our minds aren't totally hidden from each other. We can see each other's minds, in a sense, through our actions, expressions, and interactions.
So all these different ideas, ecological psychology, connectionism, phenomenology, they come together to form what we now call embodied cognition.
Right. It's not so much a single theory, but more like this big research program with the unifying idea. The body matters for how we think, and traditional cognitive science has overlooked that.
So within this program, what are the big areas of focus? What are the main things embodied cognition researchers are digging into?
Well, there are three themes that really capture the main areas of research and debate.
Get me with those themes.
The first one is conceptualization. This is the idea that our bodies actually shape the concepts we can even form. The way we understand the world is limited by our physical structure, senses, actions. So, if you had a radically different body, you'd probably understand the world in a completely different way.
Like a creature with no limbs wouldn't have the same concept of grasping that we do.
Exactly. Then there's replacement. This is more radical. It says, look, those traditional computational ideas like symbols, representations, rules, they're just not the right tools for understanding embodied cognition. We need to replace them with something new that can account for this interplay between brain, body, and environment.
Okay, so not just tweaking the old view, but throwing it out and starting fresh.
That's the idea. And then maybe the most radical is constitution. This is the body, and sometimes even parts of the world aren't just influencing cognition. They're actually parts of the cognitive system itself.
Wow, that's wild. So not just the brain thinking, but the brain, body, and environment all working together as one cognitive system.
You got it. So those three, conceptualization, replacement, and constitution, they're the big themes that drive a lot of the research and debate in embodied cognition. And, they're not always separate. They can overlap and influence each other. You might also hear about the 4Es: embodied, embedded, extended, and inactive cognition. But embodied is often used as the umbrella term for all of them. They all challenge that idea of the mind being just in the head.
All right, so let's start digging into these themes. Let's start with conceptualization, this idea that our bodies shape our concepts. How do they make that argument?
Well, a lot of the early work focused on metaphor and basic concepts. Lakoff and Johnson were big on this. They argued that we use metaphors all the time to understand new ideas, right? Like we say argument is war, and we start thinking about arguments in terms of attack and defense strategies.
It's like a shortcut to understanding something by relating it to something we already know.
Exactly. But they said not all concepts can come from metaphor. There have to be some foundational concepts that come directly from our experience, from being in the world with our bodies. Think about the concept of up. Why do we understand up? They say it's because we have these upright bodies, and almost everything we do involves our orientation in relation to up and down.
So up isn't just some abstract idea. It's grounded in the fact that we have bodies that are literally oriented vertically.
Right. And the same goes for concepts like front, back, pushing, pulling, those kinds of things. Those come directly from how we interact with the world physically. They even said, and this is a quote, almost every movement we make involves a motor program that either changes our up-down orientation, maintains it, presupposes it, or takes it into account in some way.
So our bodies kind of provide the building blocks for our understanding, and then more abstract concepts are built on top of that.
Yeah, their argument is that because those less basic concepts are built on these bodily-based foundations, all our concepts carry the mark of our physical form. They said, the peculiar nature of our bodies shapes our very possibilities for conceptualization and categorization, and it makes you wonder, how would a creature with a totally different body understand the world?
Right, like how would a spherical being understand up?
Exactly. It's a fascinating question. But, not everyone agrees with Lakoff and Johnson. Some people find their claims a bit too speculative. There's another approach to conceptualization that's more empirically focused. It says that our concepts are actually made up of sensoromotor information. So information about how we perceive and interact with the world.
Okay, so instead of lake just being a word in our heads, an embodied concept of lake would involve the feeling of the water, the way it looks, maybe even the motions of swimming.
You got it. Barcelou, for instance, talks about perceptual symbols. He thinks when we think about a lake, we're actually reactivating those sensory and motor areas in our brain that were active when we were actually at a lake. So the concept is tied to those experiences, those sensations. He says lake means something like thing that looks like this, sounds like this, smells like this, allows me to swim within it like this.
So it's like our concepts are made up of these little snippets of past experiences.
In a way, yeah. And there's some really cool studies that support this. Like, have you heard of the orientation-dependent spatial compatibility effect?
Can't say I have.
Right, it's a mouthful. But basically, Tucker and Ellis did these experiments where people had to judge whether an object was right side up or upside down.
Okay, sounds simple enough.
It was, but they found that people were faster to respond if the object's orientation, like whether the handle of a pan was pointing left or right, matched the hand they were using to respond.
Wait, so even though the handle direction didn't matter for the task itself, it still influenced their response time?
Exactly. It suggests that just seeing the object was subtly activating motor responses related to grasping it.
That's so cool. Like just seeing the pan made their brain think about how their hand would grab it, even though they didn't have to actually grab it.
Right. It's like our understanding of the object is tied to how we interact with it, even when we're not actively interacting with it. Then there's the action-sentence compatibility effect, which is even cooler. Glenberg and Kashak, they found that people were faster to judge whether sentences like open the drawer or close the drawer made sense if they responded with a hand motion that matched the action.
So if the sentence said open, they were quicker to respond if they moved their hand away from their body.
Exactly. Like their brain was already primed to do the action just from reading the words. It suggests that our understanding of language is somehow tied to our motor experiences. And there's even neurological evidence for this. Like reading action words actually activates motor areas in the brain. And if you use TMS to temporarily disrupt activity in those areas, it can mess with people's comprehension of those words.
Wow. So there's this really tight link between our actions, our perceptions, and even our language. But surely there are some folks who push back against this whole embodied concept idea, right?
Oh, of course. One argument is that, maybe we're seeing those sensoromotor effects, but they're just part of our conception of something, not the core meaning of the concept itself.
Okay, what do you mean by conception versus concept?
Think about the word bachelor. The concept is just unmarried male, right? But our conception of a bachelor might be someone who's young, lives alone, goes out a lot, you know? Those are all associations we have, but they're not part of the actual definition. So the critics are saying maybe the sensoritis effects we see are just associations, like those extra details in our conception, and not actually part of the core meaning of the concept.
So just because we usually grab a pan a certain way doesn't mean grasping is baked into the definition of pan.
Exactly. Then there's folks like Mahon and Karamatsa who say, well, maybe that motor activity we see is just a byproduct of spreading activation in the brain. Like when you process the word kick, sure, maybe your motor areas light up a bit, but that doesn't mean the concept of ticking is stored in those motor areas. It could just be that processing the word triggers a cascade of activity that happens to involve those areas.
Okay, so they're saying it's more about how the brain is wired up, not that the concept itself is embodied.
Yeah, that's one way to look at it. And then there's the big one, the challenge of abstract concepts. How do you explain things like democracy or justice in terms of bodily experiences?
Right, those don't seem like they have any clear sensory or motor components.
And that's a real sticking point for some folks. Barcelou has tried to argue that even abstract concepts have some grounding in our experience, but it's definitely a debated topic.
Okay, so that's conceptualization, the idea that our bodies are involved in shaping our very understanding of the world. Now, let's tackle replacement. This is where things get really radical, right?
Oh, yeah. This one is a big challenge to the computational view. Replacement says we need to get rid of those traditional computational concepts altogether, like symbols and rules. They're just not up to the task of explaining embodied cognition.
So it's not enough to just say the body matters. We need a whole new way of thinking about how the mind works.
Exactly. And this is where the influence of ecological psychology comes in strong. Remember Gibson and how he emphasized direct perception and action? That fits in well with this idea of replacing traditional concepts. And connectionism plays a part too, by offering those alternative computational models that don't rely on symbols.
You mentioned robotics earlier. How does that fit in with replacement?
Well, early AI was all about that classic computational approach. Think of Shaky the robot. It would sense its environment, build a model of it in its mind, make a plan based on that model, then execute the plan. Very step by step.
Very deliberate, very planned out.
Right. But Shaky was slow, clunky, couldn't deal with unexpected stuff. And then Rodney Brooks came along and said, we're doing this all wrong. He built these robots, like Alan, that were based on this idea of subsumption architecture. Imagine instead of one central brain, you have all these little modules, each controlling a specific behavior. Avoid obstacles, wander around, explore new things.
This is good. Instead of planning everything out, it's more like reacting to the environment in real time.
Exactly. And these modules, they're directly connected to sensors and motors. They can interact and even override each other. So the robot can exhibit some surprisingly complex behavior without needing to build this big, detailed model of the world in its head.
So no internal maps, no grand plans, just reacting to what's happening around it.
Brooks famously said these robots use the world as its own model, and their behavior is perception to action directly. The idea is that by being in the world, constantly sensing and acting, you don't need to create a separate representation of it.
That's a pretty radical shift. And I know some embodied cognition folks see this as a model for how biological cognition might work too, right? Yeah. That maybe we don't rely on internal representations as much as we think we do.
Yeah, some philosophers like Camero, Hutto, Mayin, they've been really influenced by Brooks's work. They argue that a lot of our everyday cognition might be similarly direct, non-representational, but not everyone's convinced that those robots are totally representation-free. Some folks say, well, even the raw sensory data or the signals going between those modules, that could be a kind of representation, even if it's not symbolic.
Right, and there's the question of how well this approach scales up. Can you really explain complex thinking, planning for the future, abstract thought, without some kind of internal representation?
That's the big challenge for this view. Critics, like Shapiro and Mathen, say as soon as you move past really basic behaviors, you need some kind of internal model, some way to represent things that aren't right there in front of you. Like, how can an animal find a new route without having some mental map of the landscape? And Clark and Toribio, they talk about representation-hungry tasks, things like imagining things that don't exist or thinking about what might happen. Hard to see how you can do that without representations.
Okay, so Brooks and robotics have really push this idea of replacing traditional concepts, especially representation.
Yeah.
What about those dynamical systems approaches we talked about before? How do they fit into this?
Dynamical systems theory offers another way to move away from that computer metaphor. Remember Van Gelder's analogy of Watt's centrifugal governor? It controls the speed of a steam engine just by constantly adjusting itself based on feedback. No need to represent the speed or calculate anything. It's all about these interconnected parts influencing each other's rate of change.
So instead of the brain working like a computer, it's more like this flowing, constantly adjusting system.
Yeah, that's the idea. And the math of dynamical systems with those differential and difference equations gives us a way to model that flow. And it's not just about the brain in isolation. You can use it to understand those interactions between brain, body, and environment. One really cool example is the Haken-Kelso-Bunce model, or HKB model. It describes how people coordinate their movements, like when you wag your fingers back and forth.
Okay, I think I can picture that.
So you can wag your fingers in sync, or you can have them going opposite each other. And what's cool is, as you speed up, the model predicts that you'll spontaneously switch from one pattern to the other. And they actually see that happen in real life.
So the model is predicting how people's behavior will change without needing to say anything about rules or representations.
Right. It's all about how those movements unfold over time as a system. And it's not just finger wagging. Researchers like Esther Seelan and Linda Smith have used dynamical systems to study how babies learn to walk. They focus on the interactions between muscles, balance, sensory feedback, instead of saying there's some pre-programmed plan in the baby's brain. And Randall Beer has used dynamical systems to model how simple agents can learn to categorize things just by interacting with their environment. The idea is that cognition emerges from these continuous back-and-forth interactions between the brain, body, and world, not from step-by-step computations based on representations. As Thielen and her colleagues put it, to say that cognition is embodied means that it arises from bodily interactions with the world.
So this is definitely a very different way of thinking about the mind. But I'm guessing this approach has its critics, too.
Of course. One big question is, can it really handle all the complexities of human cognition? Sure, it might explain finger wagging and infant stepping, but can it explain abstract thought, planning for the future, all the stuff that seems to require more than just reacting to the environment? Some critics, like Shapiro and Mathen, aren't convinced.
Right. It goes back to that scaling up problem.
Exactly. And then there's the question of whether these dynamical models are really explaining things or just describing them. Can those equations really tell us why we think the way we do, or are they just describing the patterns of activity we see? That's a big philosophical debate. Some folks, like Shapiro and Beer, say that if the models can predict behavior and handle counterfactual scenarios, what-if questions, then that's a sign they're doing more than just describing. But others, like Dietrich and Markman, they say, hold on, maybe they're just really sophisticated models, not true explanations.
Okay, so some debate about the explanatory power of those models.
Yeah, and even within the dynamical systems camp, there's disagreement about whether representations are completely gone or whether they might still play some role. It's a complex area, but overall, dynamical systems theory provides a really interesting way to move away from that traditional computational view and think about cognition in a much more dynamic, interconnected way.
Okay, so replacement is all about finding new ways to understand cognition, challenging those old ideas. And that brings us to our final theme, the really radical one, constitution.
This one says that the body and environment are more than just influences on cognition. They are actually parts of the cognitive process. It's like saying your hands or the tools you use are literally part of your thinking process.
That's a huge departure from how we usually think about thinking.
It is. Think about baking a cake. The flour, the sugar, the eggs, those are constituents of the cake. They become part of it. But the oven, that's just a causal factor. It helps the cake bake, but it's not part of the cake. Constitution says the body and environment are more like the ingredients, not the oven.
Okay, I'm starting to get the picture, but what's the argument for this? Why think things outside the brain could literally be part of our thinking?
Well, one argument comes from dynamical systems theory. Remember how it emphasizes those tight interactions between brain, body, and environment? Some folks argue that when things are that tightly coupled, they should be considered as a single system. Camero even talks about the animal and environment as one system, not separate entities that just happen to interact.
So it's like they're so interconnected, they can't really be separated.
Right. And in the math, the way those differential equations are set up, the organism and environment are all mixed together. So in a way, the math itself suggests this kind of unified system. But even beyond the math, people like Andy Clark talk about continuous reciprocal causation. He uses the example of writing. He says the pen, the paper, the act of writing, they're not just tools that help us think, they're actively involved in how our thoughts are formed. It's like this constant loop between brain, hand, paper, and back again.
So writing something down isn't just recording a thought, it's actually part of the process of thinking.
That's the idea. And that leads to the idea of extended cognition, that our cognitive systems aren't just our brains. They can literally extend out into the world, include the tools and things we interact with. But of course, not everyone buys this. Adams and Aizawa, they famously raised this objection called the coupling constitution fallacy.
What's that all about?
Well, they say just because two things are connected, even tightly connected, doesn't make them part of the same thing. Like a bowling ball and the pins. The ball causes the pins to fall, but the pins aren't part of the ball, right? They're separate things. So they say tools like a pen and paper or even Otto's notebook, they're just aids to cognition. Like the bowling alley is an aid to bowling. They're not part of the process itself.
Okay, so they're pushing back against this idea of things outside the brain being part of our cognitive machinery. What do the extended cognition folks say to that?
Well, they say the kind of coupling that matters for constitution is more than just a simple causal connection. The external element has to be actively involved in the cognitive loop, contributing to how the task gets done. Like the sound of the pencil scratching on paper, that's causally connected to writing, but it doesn't really influence your thoughts in the same way that seeing the words you're writing does. And they also point out that they're not saying the thinking itself happens in the external thing. It's more that the external thing becomes part of the whole system that's doing the thinking.
So it's about how things work together, even if they're physically located in different places.
Right. Then there's another way people argue for constitution, through this idea of parity and wide computationalism.
Okay, break those down for me.
Parity is the idea that if something outside the brain is doing the same job as something inside the brain, then we should consider it cognitive regardless of where it's happening. Think about Otto and his notebook. He has Alzheimer's and uses the notebook to remember things. Clark and Chalmers say, look, that notebook is doing the same job as Inga's memory, which is totally inside her head. So why should we treat them differently just because one is external?
So it's about functional equivalence, doing the same job even if the physical stuff is different.
Right. And then Wilson, he talks about wide computationalism. He says we shouldn't think of computation as being limited to the brain. When we use a calculator or even pencil and paper to do math, we're offloading some of that computation onto external tools. And since those tools are necessary for the computation to happen, they become part of the cognitive process.
Interesting. But I'm guessing Adams and Aizawa wouldn't be on board with this either.
You know it. They say, look, extended systems are all over the place. They can involve any tool or anything in the environment. That's just too messy for a good science of cognition. And they have this idea of marks of the cognitive, characteristics that something needs to have to be considered genuinely cognitive.
Okay, what are these marks?
One is that cognitive states need to have what they call intrinsic content. That means the meaning of the state comes from within the system itself, not from someone interpreting it. They say, look, the words in Otto's notebook, they only have meaning because Otto can read them. The ink itself doesn't have meaning.
So they're saying there's a difference between something having meaning because it's interpreted and having meaning because it's inherently meaningful.
Exactly. But Clark, he says, well, how much intrinsic content do you really need? Even in the brain, there might be processes that don't have fully intrinsic content. And he says, the Otto plus notebook system as a whole does involve intrinsic content in Otto's brain when he reads and understands those notes.
So it's a debate about how much meaning needs to be there and where it has to come from.
Right. And then Adams and Aizawa also say that a good science of cognition needs to study a relatively similar kind of stuff. They say extended systems are too varied, too heterogeneous. You've got brains, notebooks, tools, all sorts of things. That's not a unified category.
So it's not just about whether something can be considered cognitive, but whether it makes sense to lump all these different things together under the same scientific umbrella.
Yeah, and Rupert, he made a similar point. He said Otto and Inga might get to the same answer about where the museum is, but the processes they use are so different that they shouldn't be considered the same kind of cognitive process. He thinks it's better to say that the brain embeds itself with tools rather than those tools becoming part of the cognitive system. He has this analogy of an axe. You use an axe to chop wood, but that doesn't make the axe part of your arm.
Right. It's a tool you're using, but it's not part of you.
Exactly. But Clark, he says, the brain doesn't really care where the cognitive work gets done. It just wants the job done efficiently. So he sees the brain as this kind of architect that builds these cognitive systems, and those systems can extend beyond the brain itself.
Interesting. So it's not so much about the physical location, but the functional role that matters.
Yeah, and he says that focusing too much on where things are happening physically can make us miss those important functional similarities. But then Shapiro, he raises another interesting point. He says, look, a lot of these arguments for extended cognition rely on functionalism, the idea that what matters is what something does, not what it's made of. But he says embodied cognition is supposed to be about the importance of the body. If it doesn't matter whether something is made of neurons or paper, then what's so special about the body?
Okay, so he's saying there's a tension between these two ideas. If it's all about function, then why does embodiment matter?
Right, it's a good point. So constitution is definitely the most philosophically challenging theme in embodied cognition.